So today's session will be a revision session. So we will start discussing a few questions which were told as some of the doubts. Uh, so to start with, one of the doubt was about filters. How to design the filter, say in case of Butterworth, a maximally flat Butterworth filter. Say if it is being told that the order is given and the cutoff frequency is given, and then how do we design the components, that is the L and C components required. So to start with, let me just give you a brief idea of, say, this could be said as a source. Then you have G naught, and then suppose you are realizing a low pass filter, then the configuration would be something like this: G1, G2, G3, and so on. And the last element would be Gn plus 1. Okay, and that n will be the order of the filter. N will be the order of the filter. And Fc is the cutoff frequency. Okay, so this will be called as G2, this will be called as G3, and so on. So suppose if the order of the filter is n is equal to 2, then we will have G1, G2, G3. So G3, Gn plus 1 will be the last element. So G2 plus 1, G3 will be the last element. Suppose if the order is 3, then G1, G2, G3, G4. So this will be the G4 will be the last element. Okay. Now the other thing I wanted to talk about was this, based on the order of the filter. See, look at this table. This is specifically for a Butterworth filter, maximally flat. That is one of the characteristic of a Butterworth filter. Low pass filter prototypes with G naught equal to 1. So in this order from 1 to 10. So suppose, so in examination or assignment questions, you are supposed to look into the table uh, uh, based on the order of the filter. You have to choose G1, G2, G3, etc. Okay, so suppose if I am saying that the order of the filter is 2, then I have to take G1, G2 and G3. So I have these values from this table. So in examination, this table would be given so that you extract the values, or directly the value of G1, G2 will be given to you. Then if order is 3, then if for an order 3, G1 is 1, G2 is 2, G3 is 1, again G4 is 1. Okay, so for order equal to 2, G1 is equal to G2 is equal to 1.4142, G3 equal to 1. I hope this table is clear. So from this table, we will be able to take for any order of the filter what will be the G1, G2, G3, etc. So this table is particularly for Butterworth low pass filter. Okay, that has to be kept in mind.
Madam, we have to keep.
Hello?
Madam, madam, we have to keep remember that values, n equal to 2 and n equal to 3, that is G1, G2 values.
You don't have to remember these values. This table will be given to
Okay,
you.
madam.
for the examination.
Okay, madam.
Okay.
Okay, madam.
Or maybe directly the value of G1, G2 will be given to you in the as a information in the question.
Okay, madam.
Okay. Now let's start with how do we look at the equation. So first, okay, let me write it down here only. So for example, if you have order of the filter n is equal to 2. So you have G1, G2 and G3. Okay. Now, you know that there is one capacitor, then one inductor, then again one capacitor. So what do we do is we evaluate the value of capacitor. How do we evaluate the value of capacitor? Capacitance C is equal to G1 divided by Z0 into omega C. Okay, Z0, or we can call it as R0 also. Okay, so this R0 or Z0 is the source impedance, which is 50 ohm here. Okay, so G1 by, so the value of G1 divided by R0 into omega C. Omega C is nothing but 2 pi Fc, where Fc is the cutoff frequency given in the question. Okay, so this is this is how we calculate the value of capacitance in case of a low pass filter in this in this configuration. Now, going back to how do we calculate inductor value. Z naught or R naught. Okay, let me write it as R naught. R naught into G2 divided by omega C. Okay, so suppose if n is equal to 2, from this table we know the value of G1 and G2. So what do we do is G1 is 1.4142, same as G2 also 1.4142. Substituting this value 1.4142 divided by 50 into 2 pi Fc is 2 gigahertz, 2 into 10 power 9. So if you substitute for these values, you will be getting for 2 gigahertz. Just a moment. Yeah. So you should be getting the answer as 2.25 picofarad. Okay. 2.25 picofarad. So similarly, calculate for inductor value. So I'll wait for some time. I request you to calculate 50 into 1.4142 divided by 2 pi into 2 gigahertz.
Sorry, madam. 5.6 into 10 power minus 9, not giga. 5.6 into 10 power minus 9, madam.
Okay, just a minute. So 10 power minus 9 would be nano Henry.
Nano Henry. Okay, madam.
Yes, your answer is right. It would be 5.626 nano Henry. Okay. Now, going on to your specific question in assignment. So in assignment, the question was consider a second order low pass filter. So n is equal to 2. So it is clear that we have to have G1, G2, G3. But you see the cutoff frequency value is 1.5 gigahertz and the question is on calculating the inductance.
Order
So could you get the value
two,
for inductance in the same way?
2 minutes, madam.
Ah, okay.
2 minutes, madam.
Okay,
I am
I'll
charging,
wait
madam.
for
2 minutes.
that. I'll wait for that.
So 7.5 nanohenry, madam.
Right answer. So that is the right answer here.
Okay, madam.
7.5
Thank you, madam.
nanohenry. Okay. So I suggest
Okay,
you to
madam. Thank you.
practice one more question. So say
Okay,
for
madam.
example, for order n equal to 3. Okay.
Okay,
So
madam.
I request you to try this one. For consider order n is equal to 3. So G1 value will be 1, G2 value will be 2, G3 value will be 1. Okay. Can you
Okay,
calculate the
madam.
value of capacitance and inductance from G1, G2?
Okay, madam.
I'll wait for you to answer.
Okay, madam. Madam, formula is that same formula.
Same formula. So I just wanted you to just
Okay,
practice
madam.
for
Okay,
n equal
madam.
to
Okay,
3.
madam.
N equal to 3 and assume the cutoff frequency as 2 gigahertz.
Okay, madam. Madam, impedance, what we have to keep, madam? Source
Please take it
impedance,
as 50
50.
ohm. Please take it as 50 ohm
Okay, madam.
because I have worked out example for 50 ohm and 2 gigahertz. So I can compare your answer. We can compare the answers.
Okay, madam. 10 to 2 divided 2 by 2. Madam, inductance value 7.9 nanohenry.
Correct.
Okay, madam. Capacitance value 1 kilo. Madam, 1.6 nanohenry. Sorry, 1.6 picofarad.
Correct. So
Okay.
in this question, one thing you have to remember, is the formula for inductance and capacitance. So no need to remember anything else. Of course,
Okay,
you have
madam.
to remember the configuration of the low pass filter. Like it will be like a pi network, like C, L, and C. And then you have to remember only the equation for calculating inductance and capacitance from the corresponding
That
G
is
values. So this G values will
okay,
be
madam.
from the table, or it will be directly given in the question.
Okay, madam.
Now, so this was one of your doubts. The next question I would like to discuss will be the question
That the
number.
power divider, madam.
Yes, yes, yes. I'll discuss that one.
Uh, Madam, when you are teaching, no, I am understanding, madam. After that, a
Hmm.
different problem means somewhat I cannot able to solve, madam. That is the problem. That
Uh-huh.
first question, same thing only, madam.
Okay.
But your teaching is very nice, madam. But
Mm-hmm.
another model means it is very difficult to. I don't know how to think, madam.
Mm-hmm. Okay, okay, okay.
Okay.
So, first question. Okay. In assignment 6, you had asked the doubt in first question, where you have the
Yes, ma'am.
power
That the power
division.
divider, madam.
Huh. So, so I'll just draw that. So this is port 2, this is port 3, and this one is port 1. So port 1 is Z0, port 3 is 3Z0, and port 2 is Z1. Okay. So the question is, in this power divider circuit, Z1 is chosen such that when power fed from port 1, power at port 2, so power at port 2 is double that of the power at port 3. So I can write power at port 2 is equal to 2 times power at port 3. Now the question is to calculate the reflection coefficient at port 1. Okay. So now let us first look at how do we divide power such that in this port you will get double that as that of the third port 3. Okay. So first of all, let us write what is power at port 2. So it can be written as half into V square by Z1. Okay. So don't get confused with this. This is the power equation. From the power equation, we are writing this. So if you remember the previous derivations in that particular uh, portions, it is there. So you can refer to that. So it is half V square by Z1. Then you have P3, so power at port 3, which is half V square by 3Z0. Okay, so 3Z0 is the impedance at port 3. Now what do we do? I have to write that P2 is 2 times P3. So half V square by Z1 is equal to 2 times 1 by 2 V square by 3 Z0. Half and half gets cancelled. V square gets cancelled. Now what remains is Z1. We have to identify what is the Z1. The question is what is Z1? So Z1 will be 3Z0 by 2. Okay. So suppose if you connect half of the impedance here, then double power will be at port 2 you will have double the power as that of port 3. So finally this is the final condition. If this is 3Z0 and if this is 3Z0 by 2, then power at port 2 power at port 3. So power at port 2 will be twice as that of the power at port 3. And this is port 1. Hope this is clear. So now, how will you calculate the reflection coefficient at port 1? Okay. So now we know that Z1 is 3Z0 by 2. So this is 3Z0, this is 3Z0 by 2. So these two will come in parallel. Okay. So two impedances in parallel. How do we evaluate? 3Z0 parallel with 3Z0 by 2. So it's like R1, R2 by R1 plus R2. So while doing this calculation, while simplifying, you will get it as 3Z0 into 3 by 2Z0 divided by 9 by 2 Z0. Z0 will cancel, 2 will cancel, 3 and 9 will cancel. So finally the answer will be Z0. Okay. So these two in parallel will give you Z0. Now that Z0 is coming here. So the equivalent impedance is Z0. Now what is the input impedance of this line? That is again Z0. Okay. So how do we calculate the reflection coefficient? ZL minus Z0 by ZL plus Z0. Now what is the load here? The load is Z0 here. So Z0 minus Z0. So that becomes 0. So the reflection coefficient is 0. Is this clear?
Yes, ma'am. I'm clear, ma'am.
Okay. So power divider, always remember, write down the equation for power. Then based on that you can say what should be the impedance value required. Then suppose you have two different impedances at port 2 and port 3. You have to take a parallel combination such that we'll get the equivalent. Then that will be like a load. Then load impedance minus characteristic impedance will give you the reflection coefficient. Okay. Now moving on to the second question of power divider. So in second question it is slightly different.
Resistor, madam.
So in second question you have only one difference. In the port 1 you have a what you call lambda by 4 line. Okay.
Yes, ma'am.
So it is like Z1, Z1. So in port 1, at port 1 you have the impedance is Z0. Then this is also Z0, this is also Z0. This is written as Z1. Okay. Now value of Z. So here, so this is Ez and that is root 3 by 2 Z0. Okay. Now, okay, let us read the question. For the power divider circuit shown in the figure, value of Z. So this value of Z is given. And the port 1 is matched. Okay. What is the meaning of port 1 is matched? Reflection coefficient will be 0. Okay.
0.
So how do we write it? ZL minus Z0 equal to 0. So ZL equal to Z0. Okay. Now I can say whatever be the equivalent impedance here, that is equal to Z0. Okay. For that, what should be the value of Z1? That is the question. Okay. So let us look at the question. So here you have a resistor. Then you have the impedance Z0. So at port 2, and port 3, it's like Z1 plus Z0. So at port 2 you have Z1 plus Z0. And at port 3 also you have Z1 plus Z0. So what do? We take the parallel combination. So what will be the equivalent? Z1 plus Z0 divided by 2. That will be the equivalent. And that equivalent is nothing but the load. Okay. So, ZL is equal to Z0. So, that load should be Z0 for reflection coefficient to become 0. So, ZL equal to Z0. So, what do we do? Z1 plus Z0 by 2 is equal to Z0. From that, you can deduce. Okay, just a minute. I made a small mistake here. Okay, we forgot the fact that this is a lambda by 4 transformer. Okay, so how do we do? The quarter wave transformer impedance is equal to square root
Root of
of
Z0
Z0 into ZL. So here it is mentioned that quarter wave impedance is root 3 by 2 Z0 is equal to square root of Z0 into ZL can be substituted as Z1 plus Z0 by 2. Okay. Now, easy way to do it is square on both sides. Okay. So, 3 by 2, 3 by 4 Z0 square is equal to Z0 into Z1 plus Z0 divided by 2. So, Z0, Z0 will cancel. 4 and 2, this will become 2. So, what will be the final answer? Z1 is equal to 3 by 2 Z0 minus Z0. So, this will be Z0 by 2. Is this correct?
Correct, madam.
Okay. So, I hope you understood how it came. So,
Yes, now clear.
I will give a brief of that. So, you take port 2, port 3. Okay. Take the equivalent. So, port 2 in parallel with port 3, you take the equivalent. So, that equivalent impedance is nothing but the load. Now, between the load and the port 1, you have a lambda by 4 line. So, apply that equation for a quarter wave transformer. That's all. So next I will move on to your doubt in the fourth question. In the same assignment 6, I will move to fourth question. So in fourth question, the question is so about a Wilkinson power divider. So Wilkinson power divider means, so here you have port 1, there is a lambda by 4, another lambda by 4 line, and this is port 2, this is port 3, and between these two ports you connect a resistance that is 2 times Z0. Okay. Now the question is, if the resistance between port 2 and port 3 of a Wilkinson power divider is removed, okay, if this is removed, what will be the reflection coefficient at port 1? Okay. For this question, this is a conceptual question. We have to understand that at any cost in a Wilkinson power divider, port 1 is matched. Okay. Irrespective of what is connected at the between the port 2 and port 3, the reflection coefficient of a Wilkinson power divider at port 1 will be 0. Okay. Now, second thing, what is the purpose of this resistor connected between port 2 and port 3? So, this will act as an isolation between port 2 and port 3. So, because this is connected, because 2Z0 is connected, we get S23, S32 is equal to 0. Okay, so there is this resistance 2Z0, which is connected between port 2 and port 3, gives an isolation between port 2 and port 3. It has nothing to do with the reflection coefficient at port 1. So that is the key point here with respect to Wilkinson power divider. I hope this is clear.
Oh, okay, ma'am.
So your doubt in assignment 6 is over. So I'll move to assignment 4. Okay, in assignment 4, first I will start with the 7th question. That is about a two-section binomial transformer. Okay.
Yes, ma'am.
I will explain you like how the binomial transformer is, and then we will try to solve the question.
Okay, madam. Madam, that formula is there, madam, but I seen that videos, but last answer I don't know how to find out. C power 0 power 2 is there, no? That
Oh,
how
okay,
I don't
okay.
know how to simplify this.
Okay, okay. That I
I
can
seen
explain.
your
I
previous videos also seen, madam. That also not there. Only you
okay,
written
okay.
formula after that that's the problem. Okay, madam.
Okay, okay. That we can that I can explain now in this class. Okay. Okay, let me first start with the question. So it is a binomial transformer. So in case of a binomial transformer, say if it is two-section binomial transformer. So suppose this is section, say this is section 1 and this is section 2. So what does it mean? Suppose you have a load ZL and you need to match it to Z naught. Okay. In two-section binomial transformer, first ZL will be matched to one particular, I mean in an intermediate impedance, and then it will be matched to Z naught, not the direct matching. Okay. So it is a two-section binomial transformer used for matching. So here in the question of assignment 4, the numbers are ZL is 200 ohm and Z0 is 50 ohm. Okay. Now the characteristic impedance of the section 1 and section 2. So that is Z1 and Z2. This is being asked in the question. Okay. Now as per the formulas what I have given. So this formula you have to remember. So for this is the common formula. Okay. Now, in this formula, how do we evaluate the Cn raised to minus n? Okay. So that is your doubt. To evaluate that, you have to take n factorial. So this capital N is the number of sections and small n is the section, okay, small n is the section number and capital N is the total number of sections. Okay, don't confuse that. Capital N is the total number of sections in the binomial transformer and small n is the section number, whether it is first section or second section. So this formula will be n factorial divided by n minus n factorial into n factorial. Okay. So if you remember this one, this factorial you know. So you have to just take the factorial of that number, whatever it is. So same
Yeah, I
answer.
know, madam. I know
So
that.
for example, if you, I suggest you please try out an example so that we can verify if we are getting the same answers. Okay. So let us first evaluate section 1. Okay. So for section 1, ln of z1 by z0 is equal to 2 power minus 2 c0 raised to minus 2. So because it is section 1, we have to keep section 1 we have to keep. Okay, let me write it that also. For section 1, n is equal to 0. For section 2, n is equal to 1. Okay, this is the uh, this is the numbers to be followed. So then ln of 200 by 50. Okay, can you find out z1 from this? First evaluate this part and then find out the z1.
Hello, madam.
Hello.
Madam, that C0 minus 2 is there, no, madam. The 2 capital N is 2, small n is 0, no, madam.
0, 0.
For example, they will put 0 factorial means 0, no, madam.
0 factorial is 1.
Oh, okay, madam.
C naught raised to minus 2. Suppose you want to evaluate C naught raised to minus 2. So what you will do is 2 factorial divided by 2 minus 0. So that is again 2 factorial. Then multiplied by 0 factorial. That is 1. So 2 factorial by 2 factorial. This is finally 1. Okay. So 2 raised to minus 2 multiplied by 1 multiplied by ln of 200 by 50.
Madam, right side answer is 0.3465.
Correct. This is 0.346. Then from that,
Okay,
you
madam.
please calculate Z1. You know Z naught is 50.
Okay, madam. 10 power. 10 power, no, madam.
Not 10 power, it is ln. Remember, it is ln. So e raised to.
Oh, okay, madam. Thank you, madam.
So this will be Z naught multiplied by e raised to 0.346. Yes, right answer. That is 70.7 ohms. Similarly, try to do for the second section. So for section 2, what will happen? ln of, it should become Z2, okay, divided by Z1. So whatever value you calculated at Z1 has to be substituted here. Okay, ln of Z2 by Z1 is equal to 2 raised to minus 2 into C1 raised to minus 2 ln of 200 by 50. Now, how do we calculate C1 raised to minus 2? C1 minus 2 will be 2 factorial divided by 2 minus 1. 1 factorial multiplied by 1 factorial. So, the final answer is 2.
2 into 0.25. Madam, right side 0.6931, 32 or 315 is that?
Correct. So, Z2
One second, madam. One 41, ma'am.
correct. So, Z2 is 141 ohms. So, that is clear, right? So, here you have to remember two equations. That is, one is for the design of the binomial transformer, and this is how do we evaluate the Cn raised to minus n.
Okay, madam. I'm clear, madam.
Okay. Now, there is one question for which, in fact, even I have a confusion. While I am trying to do, it is showing us, the answer option given as per NPTEL is not correct, it seems like. So somebody in the discussion forum has asked that question. So let us wait. Maybe the TAs for the assignment section will respond soon. So I will just show you how that has to be done. So this is question number 3 of assignment 4. So the question is like this: if Zin equal to Z0, what is the value of X? Okay, this is the question. Now, for this question, you have to understand that there is a load ZL, which is 2Z0 plus JZ0. So it is a complex load. Then you have a lambda by 8 line. So this transmission line is a lambda by 8 line. After that, you have a reactance, which is Jx. Okay. So we can use the impedance transformation equation. So we know that always we write Zin equal to Z0 into ZL plus JZ0 tan beta L divided by Z0 plus JZL tan beta L. Okay. So remember, when do we write this equation? Suppose you know that there is a load ZL and there is a transmission line length L. And this line has impedance Z0. To evaluate what is Zin at this point at a length of L. Okay. We use this equation. Now, based on this equation, let us do for this? So there is a lambda by 8 line. So what will be beta L? Beta is 2 pi by lambda into L is lambda by 8. Lambda gets cancelled. It becomes pi by 4. Okay. So tan beta L will be 1. Okay. So Zin can be written. So Zin will be the impedance here at this point. Okay. At the end of the lambda by 8 line. So that Zin will be Z0 into ZL value. I'll substitute 2Z0 plus JZ0 plus JZ0 because tan beta L became 1. Okay. Divided by Z0 plus J times ZL. Now 2Z0 plus JZ0. Okay. Now simplify this. So how do we simplify? Z0 into 2Z0 plus 2JZ0 divided by Z0 plus 2JZ0 minus Z0. Okay. So Z0 and Z0 will cancel here. 2 will cancel. Again, Z0 will also cancel. So final answer will be Z0 into 1 plus J divided by J. Okay. So 1 by J is minus J. Okay. Minus J Z0 into 1 plus J. Okay. So evaluating this, what you will get? Minus J Z0 plus Z0 or Z0 into 1 minus J. Z0 into 1 minus J. Okay. So at this point you have an equivalent. Okay. Now you have an equivalent here. The value of that equivalent is Z0 into 1 minus J. Okay. Now when we look at this terminal, so this impedance is in series with the JX. So this impedance is in series with the JX, and finally at Zin, the final value of Zin is Z0. So to get that, what you have to do, two impedances in series, what do we do? You will add it. Z0 into 1 minus J plus JX. So these two in series added together, I should get what? Zin, which is equal to Z0. I'll equate into Z0. So Z0 minus JZ0 plus JX is equal to Z0. Z0 and Z0 will cancel. So finally, JZ0 is equal to JX. So X is equal to Z0. But in the NPTEL options given, the option seems to be Z. The right answer seems to be Z0 by 2. So there is confusion here, but even if after recalculating, I feel that Z0 is the right option. Let's wait for a couple of days. I think the solutions will be recorrected. I mean, okay, so that is one point. Meanwhile, if there are any changes or updates, I will let you know.
Okay, madam.
So this is clear, right? I mean, this is just the impedance transformation. So
This is clear, madam. But your videos, no problem, madam. Your teaching is very well, madam. I have all videos.
Okay.
But some mistakes only, madam. You are teaching very well, madam. You are talented, madam.
Okay. Thank you. So I think whatever doubts you have asked, I have covered. But meanwhile, if you have anything else, you can ask any particular portion.
Yes, madam. That is satellite, madam. How to convert, madam? That kilometer. One second, madam. One second. The problem is there, madam. Kilometer. Yes, madam. Meter per second into kilometer, madam. Kilometer per hour. One problem is there, madam.
Oh, okay.
The tone only I don't know, madam. Meter per second into kilometer per hour. That one, madam. One more thing, madam. How to convert polar to rectangular, madam? That 0.3535 plus j 0.3535 is there, complex value. But
Hmm.
that S parametric value is for in terms of polar form, madam. I don't know how to convert that polar form to rectangular. That two only, madam.
Okay, okay, okay. Huh, huh, huh. So let me address your first question. How do we convert meter per second to kilometer per hour? Okay. So
Yes, ma'am.
the easy way here is, remember, you know the conversion of meter to kilometer. Divide it by 1000.
Oh,
Correct? Or multiply by 10 power minus 3. So we are converting meter to kilometer, multiply by 10 power minus 3. So this is in the numerator. So meter and kilometer is in the numerator part. Now in the denominator part, you have per second converted to per hour. Okay. So how do we convert second to hour? That is the, we know that how do we convert meter to kilometer, centimeter to, so everything we know, but we have a confusion when it comes to meter per second, kilometer per hour. Okay, so the easy way is, first to understand, this is on the numerator. We did for numerator. For denominator, second to hour. So second to minute, and then minute to hour. Simple. So second to minute, what we have to do? 1 minute is 60 seconds. So divide it by 60. 1 by 60. 1 hour is 60 minutes. Again multiply this 1 by 60. Okay.
okay, madam.
So whatever number you have, multiply with this. So this is in the denominator, this is in the numerator. You will get the final answer in kilometer per hour.
Answer came, madam.
Okay, okay. Now,
Thank you, madam.
polar to rectangular and rectangular to
Yes,
polar
ma'am.
conversion.
That one.
I think in your examination you are allowed with a scientific calculator or screen calculator. I think it is a screen calculator.
That one mail is came, madam. That online calculator, we have to use online calculator like that.
Oh,
One mail
okay.
came.
Okay, okay. So in that case, the scientific calculator, online scientific calculator, you can check. Uh, um, then it will be is it the TCS ion? I am not sure which one they'll give you for examination. Mm,
Madam, for example, 0.6, 0.6 angle part is 45 degrees there, na, madam. How to convert, madam? One small value you tell, madam. Remaining I will
oh,
follow.
okay. 0.6 angle 45 you are saying.
45 degree means how to convert to complex value, madam, rectangle value.
Okay. So if you had the scientific calculator which can directly take polar of or rectangular of, that is the easiest way. If you don't have that, what you do, this is of the form r angle theta. So just a moment, I will write the equation for you. So I will write the general form first. Suppose you have a plus jb. This is rectangular form. So suppose you want to convert it to polar. So it will be like this. Square root of a square plus b square will be what? R. Okay. Now, so this is R. We found the R. Now, how do we find theta? Theta is tan inverse of b by a. Okay. So now you know how to convert rectangular to polar. Is that okay? A plus jb. How do we convert to r angle theta? Square root of a square plus b square will give you r. Theta will be tan inverse of b by a. Okay.
Okay, madam.
Okay, no. Similarly, do the reverse conversion for polar to rectangular. So I'll write in a sheet. Okay. So polar form, suppose it is r angle theta. So what do we do is r cos theta and r sin theta. Okay. So this will be the real component and this will be the imaginary component. Okay. So this is A and this is B. So wherein I will finally write it as A plus JB. So from r angle theta, you make it r cos theta, r sin theta. That will be your real and imaginary component. Finally, you will write it as A plus JB.
Okay, madam.
So that is simply how do we evaluate like rectangular to polar and polar to rectangular. So suppose if your calculator supports, you can directly take like this polar of this complex number. If it doesn't support, you can use this format. How do we evaluate? For example, in this case, polar, how do we evaluate? Square root of 0.35 square plus 0.35 square. So that will be R. And theta will be tan inverse of B by A. So B and A are same. So tan inverse of 1 it will come. So that is pi by 4 or 45. Okay, right?
Okay, madam. Thank you, madam.
I think your doubts, any other particular doubts you have, you can ask. So for today's session, somebody
No, madam.
joined now, Amit Kumar. So if you have any doubts, please ask. So I was taking the session from 6 o'clock. So a few questions had been, there were few doubts. So I had been solving those questions. So if you have any particular questions or any portions which you want to revise or something, I can do that. Are there any of the portions or sessions of this whole course, any of the assignment questions? If you have anything to ask, even simple calculations questions you could ask. Hello, Amit. Are there any questions?
No, ma'am. Ma'am, can you please share your email ID if any type of
Okay.
doubt can I ask?
Okay. Okay. Um, so this is my email ID. Uh,
Thank you, ma'am.
okay. And meanwhile, if there are any questions, basically the solutions are up for all the assignments. So maybe you can look into the questions and solutions and see if at all there are any mistakes. Kindly point it out at the earliest, so that the assignment can be recorrected or reevaluated, whatever be the case. So may I know when is the examination date?
I think, ma'am, 27 or 28.
Okay, so I think you have a time of 1 week more. So, in fact, the revision class became a bit early, but I suggest if you have any questions, you can ask me in the email. Um, yeah.
Yes, ma'am, of course.
So, if you don't have any questions, we'll wind up the session for today.
Ma'am, in
Hmm?
examination, the question are like the assignments.
Yes, mostly if you could solve all the assignment questions without any help. I mean, if you have really understood how it has to be solved, then it will really help. I mean, to a large extent, you will be able to solve most of the questions. But there would be some extra, I mean, some questions which you have not seen. But I feel that it will be mostly around the assignment questions.
Okay, ma'am. Thank you, ma'am. Means questions are like assignments questions.
And one thing you can do, like while you solve the questions, you can take the help of the online calculator and practice, so that you will have a handy, I mean, you will be able to do it easily in the examination also. uh, and especially the some of the charts and all will be given to you as information in the question itself, or some or the other way, so you don't have to remember that. Say for example, in case of filter design, the chart for G1, G2, G3 cannot be memorized. So those kind of things will be given in the question, so you don't have to remember that. But of course you may have to remember the design equation. How do we evaluate the order of the filter? How do we evaluate based on the insertion loss? How do we calculate the L and C values from the G1 and G2 values? So those has to be memorized. But of course, those have some easy ways to remember those equations.
Ma'am, in exam, question are based on Smith chart.
I don't think we have Smith chart in this uh, microwave engineering course. I mean, the focus of this course was not on Smith chart, I believe. Mostly the questions will be on the impedance matching with the LC networks and similar kind of things.
Okay, ma'am. Thank you.
So the recorded videos are available in the YouTube and I think in the NPTEL site as well. So if you wish to go through any time, you can just have a look at it. So thank you for joining the sessions and keeping up the spirit till the end of the course. And yeah, thank you for joining. Uh, Wish you all the best for the exams. We can be in touch. You can email me with your doubts. Yeah.
Okay, thank you so much, ma'am.
Okay.
Thank
Thank
you.
you. Bye.
Bye.
Thank you, Arun Raj. Yeah. And thank you, Amit. Bye.